I'm hoping this is going to be a short video. I wanted to deal with each of these little subtopics just outside the main video that's coming up next, so that it's extremely clear and not confusing at all. But they're important concepts. So the concepts that we're going to talk about are using functions to organize your code, using timers to make your code more efficient, and the very, very basics of data types. So we're going to start off with data types. There we go. So this is going to be data types. Now, if you're in a computer science program or you're already experienced programming, you really can skip this section. This is extremely basic. I've been using, up until this point, mostly integers, because that's just the default data type. If you look at the reference for Arduino, or the reference for C++, and many other languages, you will find in the language reference data types, talks of data types. You can skip array. Array is just a collection of individual values. So it's like you can do a Boolean, or you can have an array of 2 or more Booleans. You can have an integer all by itself, or you can have an array of multiple integers. So the array is something that you should check out, but this is not what we're talking about here. If you look at the integer data type, the integer data type is 16 bits. It's a signed data type, unless you tell it otherwise, and that allows you to go from 32,768 negative all the way up to positive 3,276.7. When you take 32,767 and plug it into an integer data type, all of the bits, all of the 16 bits are 1, and when you add 1 to that, it overflows into negative 32,768 and then continues counting up towards 0 and scrolls through. So you can't use an integer if you need to hold numbers that are larger than plus or minus 32,000. Because it's 16 bits, each integer that you declare takes up 2 bytes of your microcontroller's memory. That's important to realize, because if you start creating integers, or any variable really, if you create a large number of variables and never clean up the memory, or you keep them all global and have no local variables, then very quickly you may actually run out of memory and have to reprogram things. But it's always a balance act. So if you don't necessarily need to store a number that's 32,000, then you can actually use a smaller data type, like a byte, which is 8 bits. But because it's only 8 bits, you can only store the values 0 to 255. If you have 255, then all 8 bits are 1s. You add 1 to that, and it overflows to 0 and starts counting up again. If you need a larger value stored than 32,000, then you can use a long data type, which instead of 16 bits, uses 32 bits, and can store over 2 billion. So just as a quick demo of that, if you declare count in this simple little program to be equal to 0, and we have serial communications, and we have a button on 5 and a LED on 9 and 10, and I have code that reads the input from the push button, and if the push button is pressed, then it turns on the LED, the red LED, and it inverts by knotting the current state of pin 10 and writing it to pin 10. So we're going to push the push button, turn on the red LED, and invert the state of yellow LED whenever the push button is pressed. If the push button isn't pressed, we don't change the yellow, but we do turn off the red. We print to the serial console the current count, which increases every time we're holding the push button, and we wait 1 second between updates. What does that look like with a byte? Well, at 1 second counts, it's going to take 255 seconds of holding this push button to count. But you can see that the push button works, the LEDs work, the yellow LED is blinking whenever we're pushing the push button. If we change the delay to be 10 milliseconds, and watch the count, then you'll see it count up to 255, roll over to 0, over and over and over again. This will bite you in the butt periodically when you forget to use the proper data type. On the other hand, if we use an integer, 16 bits, reduce the delay even more. So if we start the count at 32,000, and add, when it gets to 32,767, it'll roll over to minus 32,768 and begin counting up again. If you were to make that a long variable, then you could actually store a value all the way up to about 2 billion. And I guess I already overflowed it. So what was the number there? 2147. 2147. How about we just copy that in? Important to know, partly because the timing in the big program is going to be in microseconds, and 1 second is 1,000,000 microseconds. So we're going to need longs to keep track of things. So if we now start the simulation again, and let's change that count back to 0. So if we start the simulation again, and the LEDs are off, and we push the push button, and the red LED turns on to show that we've pushed the push button, and the yellow LED inverts its state every 1 second. The code in this very small program is not super easy to read, but it's also not a lot of code. Later on, when we have a lot of code, it's going to be much more preferable to have loop be cleaner and smaller and be more of a director of activities than to actually have all of the code in loop. It'll make it much easier to read through, among other things. So let's say you know nothing about functions. You actually do know a little bit about functions right now because you've been using functions without really knowing it. There are 2 functions in an Arduino program. The first function is setup, which is a function that's called by the Arduino once when you reset it, when you upload a new program, or you apply power for the first time. This is usually used to set things up. It's used for things that only need to occur once at the beginning of your program, and then this function is never called again. After setup's done, the function called loop is called. And loop is where, in theory, everything happens. And it happens continuously until the next time you restart the Arduino, at which point setup runs once and loop gets control for the rest of its life. But that doesn't prevent you from creating your own functions. These are just the default functions that are required for an Arduino program to exist in the first place. You can make simple functions that do things, and you can call them with names of the functions that are more meaningful than digital write 10, not digital read 10. You can also use functions to prevent duplication of code by passing in parameters when you call the function. So let's say we have this code that is currently checking for the push button to be pressed, and if pressed, turns on the red LED and inverts the state of LED 10, the yellow LED. So we can take this code and we can create a function above loop for the moment, but it can be moved down by creating a what's called a prototype, which is just a warning to the Arduino that although the code doesn't exist now, it will exist later in the program. So there are a few interesting details. One is you have a return data type. Now, a lot of functions don't actually return data back to the program, but for the moment we are going to follow that convention and start off with a void return data type. Because just like with the function loop, which doesn't return anything when called, and setup, which doesn't return anything when called, if we're doing something simple like just inverting the state of an output, we don't really need to return a status to the program. So I'm going to call this, to start, invert yellow LED. I'm putting these brackets in there because they're necessary. And if I was passing information into this function, there would be something here. But for the moment, we're just making a function to do something really specific. We're not making it flexible. Like all of the other functions, we have curly braces to contain the code that executes when the function is called. And then our code goes here. So what code goes here? The code that goes here is what we want to do when the function's called. And finally, to complete this, we replace the code that is in the function with a call to that function. And for the moment, I'm going to leave the comment. So if I do nothing else in this program, I have made this little if-then loop more readable, because if this condition is true, then we do this thing to pin 9, whatever that pin is connected to. Oh look, it's a red LED. Great, wonderful. But then right here, we very clearly explain what we're doing. Call function invert yellow LED, passing no parameters to the function, just simply calling the function. Execution of the program then jumps to the function called invert yellow LED, executes the code in that function, and then when it's done, jumps back to where it was in the main program, increments the count, and continues on with its life. If we run this, the functioning of the program is exactly the same, but we've made loop more readable. And if there was a lot of code in this function, we've also made loop much smaller. Now I'm going to quickly add a third LED. Now let's say instead of just inverting the yellow LED, we want to also invert the green LED, but we don't want to copy this function and have multiple functions. Well, let's rename this function. We're going to call this function invert LED state. Invert LED state. Rather than being really specific in the function and inverting the state of pin 10, we're going to give it the ability to take a number, a reference, from the main program. So instead of giving it 10, we're going to create a variable that is just within this function, and it's going to be an integer. Integer LED pin number. Instead of saying 10, we're going to write the value to LED pin number of the opposite of the current state of LED pin number. But where does this come from? This number that we want to be 10. That's where the parameter comes in. I'm not going to change the comment just yet. I'm going to leave it exactly as it is. So now, when we detect a push button, we're turning on the red LED, and we're calling the function called invert LED state, and we're passing it a 10. That 10 is going to become the integer in the function LED pin num. So it'll be the same as digital write bracket 10, comma, not digital read bracket 10 bracket bracket. And this allows us to call this one function but pass in different values. So if we start the simulation, it still behaves exactly the same. Push the button and yellow blinks. Add a second piece of code. Same function, but we're referencing pin 11 now. Push button is pressed, red LED is turned on, and we call the function to invert the state of pin 10, followed by calling the same function to invert the state of pin 11. And if, at some point, the state of 10 and 11 were different, say the green LED, after setting the pin mode, was on, then calling those inversions would do exactly what you expect. Now you can pass a function more than just one variable. You can create a variable, another integer, just because, but any data type is acceptable. So we'll make another integer, add 1 to this number. And then within the function, after we've inverted the state of the LED, we can take that number that's passed in, increment it by 1, and print it. Since we're passing in two parameters, we now have to pass two parameters. So let's say the first one with the red LED is going to invert the pin 10 and add 1 to 3. When we invert the green LED state, we're going to add 1 to 13. So what does this look like? Well, when we call the function invert LED state, we're passing it two parameters. The first parameter is 10, the pin number. The second parameter is the number that we want to increment by 1 and print out. When it gets to the function, LED pin num takes on the value of 10, the first parameter. Add 1 to this number takes on the variable 3. We invert LED pin number. We add 1 to that variable that was passed in, and then we're going to print the new value of add 1 to this number. So the count is 0. We haven't called the function yet. We push the push button, we call the function, and now we get a count of 2, 3, 4, 5, 6, and each time the function is iterated, it's being passed a 3 or a 13. 1 is being added to the 3 or the 4, 3 or 13, and we are printing 4 or 14. Now we don't have to print this within the function. We can also pass it back directly to the calling program and then print it if it makes sense, or use it any other way we want to. So if we remove this from here and we return to the calling program the value, add 1 to this number, we have to change one other thing in this function, because now we are not returning nothing. We're not returning a void. We are returning an integer. Add 1 to this number. And finally, we have to actually do something with that number. So if we look at this loop and we look at invert LED state 10.3. Now let's say all we care about is inverting the state of the yellow LED. We don't care what the returned value is. We just want to invert pin 10. So we won't change this at all. I can declare a local variable here because it's very temporary. I can make an int returned value equal to what comes back from calling that function. So we're going to create an integer. We're going to call that integer returned value. And we're going to make returned value equal to what is returned from the function call invert LED state. And we're going to pass invert LED state two variables, 11 and 13. 11 is the pin number that's going to be inverted. 13 is going to be the value that is incremented and returned as an integer to the program that called it. And then we can print it, or we can do whatever we want with it, including printing it. And I can even double it if I want. I can do whatever I want with it. On top of that, one of the things that I like to do is I like to use defines to make a code more readable as well. So we can, for example, define pin red LED to be equal to 9. Sorry, pound define. So what this does is when the program is compiled by the Arduino software, everywhere it sees the text pin red LED, it will replace it with 9. That allows us to do a couple of things, and I think I've mentioned this in past videos, but I'm going to say it again. One is that it makes the code more readable, because rather than pin mode 9 being an output, what the heck is 9, we can replace 9 with pin red LED. Oh, okay, so pin red LED is output, and we can quickly look up here at the program, at the define, and say, okay, well, what is pin red LED connected to? The red LED is connected to 9. And if I was to need to move the red LED to a different pin, so let's say we just move pin red LED to 8, or we realize after programming a huge program that the red pin was not 9 all along, but actually 8. Then I literally just have to change the program in this one single place. And again, everywhere the compiler sees pin red LED, it will replace it with an 8. So that means that if I have it 100 times in the program, in the initial declaration, in the code that writes it high, or the code that writes it low. I only have to change it in that one location, and everything just works. And it makes the code much more readable. Again, because every time you see a 9, you don't have to wonder what 9 is or look at a schematic to see what 9 was. Yeah. Very, very valuable to use those. And while you could also declare the variable pin red LED to be equal to 8 with a semicolon, if you do that, this becomes a variable, it's held in memory, and it takes up space in your program. It takes up 16 bits of processor memory. As a define, it doesn't take any memory. So for the last part of this video, let's talk about timing. And by timing, what I'm talking about is prioritizing tasks. So there are always going to be things that are very important to do quickly and as frequently as possible. You want to monitor safety systems. You want to monitor for button presses. You want to monitor for a data logging application. You want the timing for that to be potentially very fast, but more importantly, you want it to be accurate. You want it to be somewhat deterministic. You want to be able to know for a fact that if someone walks up to your elevator and pushes the button really quickly in, say, 1/10 of a second, that the control system will register that 1/10 of a second button press and not frustrate the human into hammering it and pushing it and standing there looking funny. So when I'm talking about timing, I'm talking about making sure things happen on time, making things happen on a regular schedule, and making sure that non-essential tasks don't impact the rest of the tasks. Here I have a quick little program. 3 LEDs and 1 push button. I've defined the push buttons and such up here, so it's very, very easy and readable. I have a variable that's counting the number of times the loop executes while the button is pressed. I have 2 long variables that are going to monitor for intervals. This is going to be what we're using to decide when to do things. Every half second, every full second, 20 times a second, whatever. These variables are extremely important because these variables are the ones that actually do the timing. So in the Arduino, there are 2 lovely little functions. One is called millis and one is called micros. Millis will tell you how many milliseconds it has been since the Arduino started running the program. Micros tells you the same thing, but it's in microseconds, so you're getting 1,000,000 counts per second. When I initialize these variables, I'm initializing them to values that make sense. So current micros, the current time, the wall clock, is going to look at the current time of the microprocessor. Last micros, from the last loop execution, is going to be set to the same value. So initially the execution time is going to be equal to 0. This function from the last section you recognize. I don't care about the addition, I just care about having a function that I can call to invert an LED state. We've got the serial communications, we've got the push button, we've got a red, yellow, green LED, and we're setting the green LED high to start. For now, there's no other code for the green LED. It's being turned on in setup, and it's staying on forever until we change it. In loop, we're checking for the button press, and if it's pressed, the LED shows us the state of the push button, and we increment the count by 1. Otherwise, turn off the LED. Every time we go through the loop, we are now going to write 2 things to the serial console. One is execution time, and the other is the counts. And then we're going to, on every loop, invert the LED state for pin yellow, delay by 1,000 milliseconds. Very wasteful, because we want this yellow LED to blink once per second. Well, once every 2 seconds, but you know what I mean. Here is where the timing actually gets updated, though. So, at the beginning of the loop, current micros and last micros match the time of execution of the Arduino right there. Now we've executed some code. So now we update the current time to the current time. And at least a few microseconds have gone by. The execution time of the loop is going to be current minus the last micros. And once we have this value, we can make last micros be equal to the current time and wait for the loop to go through one more time, at which point we update the current micros, subtract, and the loop execution time is calculated again. And then these variables are going to accumulate the execution time of the loop on every loop. I'm not using these yet, so you can safely ignore them. If I run this program that has this very wasteful 1 second delay, the green LED is continuously on. The yellow LED is changing state on every loop, and every loop is at least 1,000 milliseconds. But if we look at the loop execution time, you can see that the loop is actually a little bit more than 1,000 milliseconds. It's between 1001 and 1002 milliseconds, because I have a delay that's about 1,000 milliseconds, plus the actual loop execution time of 1.5 milliseconds. Among other things, this means that if I push the push button for a half a second, there's about a 50% chance that I'm going to miss pushes. I missed that one. I missed that one. I missed that one. I missed that one. Ooh, caught one. Got another. The point is, because I have that 1 second delay, for that second, I can't check push buttons. So I want to check push buttons very, very quickly. I want to check it very frequently. But I still want to blink that yellow LED once per second. How do I do that? The best way to do it is to learn how to use timer interrupts. I think, second best and very simple way to do it is using the loop execution and measuring the microseconds, and then putting a few conditions into calling a function that does something. So, let's stop this. And instead of having a delay, we're just going to wipe this delay just gone. Wasteful delays, gone. Don't get me wrong, there are certain cases where short delays are very important, but a lot of the time they can be removed. A lot of the time, delay is a useless, wasteful command. So let's get rid of this delay entirely. And if we just run this program as is, just removing the delay entirely, now the program is running as fast as possible with the code that is currently still a part of the program. It's only taking about 730 microseconds to run all that code. That does mean that the LED is changing state over 1,000 times per second, so obviously we're not going to be able to see it. So let's flash the LED on a controllable schedule. The LED flash interval is accumulating time on every loop execution, and it's accumulating the number of microseconds that have passed. So we can grab this code and we can say if LED flash interval is greater than or equal to 1 million microseconds, so 1 second, then invert the pin. but we don't actually want to. Digital write. This is a leftover. Invert LED, invert LED state. So if the microseconds that have been passed is greater than 1,000,000, invert the state of the LED and 0 the interval since the last time it was reset. Run this code. So now we're running into limitations on the simulator because the code is trying to run really fast. If you look up here, the simulator time on the browser, you can see that it's very obviously not keeping up with 1 second per second because we're asking a lot from it. We are. The hardware would be better suited to doing this, but we can actually make this significantly better. So why is it taking so long? Why is it going so slow? Well, among other things, we're printing every single loop execution. So let's reduce that as well, because it's really not necessary. So we want to print the execution time, and we want to print the count. But as humans, we don't need to see 1,000 updates per second. So in addition to blinking the LED, we can update the user periodically as well. So instead of simply printing on every single loop, we will print every 10,000 microseconds, which is 10 milliseconds. So we're actually printing 100 updates per second, which is still ridiculous. But it's going to significantly drop the execution time of the loop here. So if we start this, instead of taking a millisecond to go through the loop, it's taking just 50-ish microseconds. And the blinking of the LED is more in line with once per second, even though looking at the simulator it's obvious that 1 second is actually about 5 seconds. Once again, as a human, I don't need this many updates per second. So let's do 10 updates per second. And that didn't impact the execution time much. It's more consistent. It's now 52 microseconds per execution, typically. And the simulator is ratcheting through about 1 second in 3 seconds. The important thing to realize is that, yes, it's not running as fast as it could on the hardware, but it is running very fast. And if the loop's execution time is only 52 microseconds, well, that means that we're checking the push button. We're checking for a push button press 20,000 times per second. We're not going to miss a push at that rate. So looking at the count, 70,000, 80,000, 90,000. Judging by that, the loop is executing about 10,000 times per second. And what if we wanted to flash the two LEDs at different rates? Well, again, equally simple. Copy the code. So now we have the push buttons being checked as frequently as possible. We have the green LED blinking at one rate. We have the yellow LED blinking at another rate. And we have the output to the human happening periodically at a rate that makes sense for the human. And the loop execution time is about 50 to 65 microseconds per loop, with not much work. And since we're basing our timing off of the actual hardware timer in the Arduino, it's going to be fairly accurate. If you wanted the ultimate in accuracy, you could also attach a real-time clock to periodically reset whatever inaccuracies in the do exist. But for short term, for short duration, not important. So how does this relate to the elevator project? Well, the elevator project has inputs. Catching the user pushing the push buttons, 1, 2, 3, 4. Doesn't need to happen frequently, but it does need to happen frequently enough for us to catch them. On the other hand, reading the feedback from the potentiometer so that the PID can do its thing needs to happen pretty frequently. And the PID loop needs to happen at some frequency that is stable. Because if the loop execution time of the PID loop varies a lot from loop to loop, we're going to have problems. And finally, whatever outputs to the user are going to happen, like indicating the floor on the NeoPixels, or lighting up an indicator that says floor 2, floor 3, floor 4, for the current status, for the current position of the elevator, or the question of whether the elevator is currently on its way up or down. Those can happen as infrequently as once a second, and no one's going to know or care.